Okay, this is 2019 problem set 1, and this is number 3. This is a very, very long problem. It's not that bad, it's just lengthy. So we've got a platform. It's sitting here. We've got an eye of the platform, IP. We've got a little motor-driven wheel underneath it that is revolving. It's touching it, so it's causing it to speed up. It's located at distance d out from the center of rotation of the platform itself. And it has a radius in the contact with the wheel with the platform without slipping. The first thing they asked me to do is derive an expression for the angular speed of the platform. And I've got to express all my answers in terms of I, R, D, F, delta T, and physical constant as appropriate. So I say, okay, so they want to know what this omega p is that I reach after this time t. So during this whole time, this little wheel is spinning, applying force. Okay, it's applying a constant force because it says it exerts a constant magnitude force F tangent to the wheel. So it's applying it here, and it does it for that whole time t. So I think of that and I say, well, this thing is spinning. So anytime that we're dealing with something that's spinning, I'm thinking torque. So on A, I know that it is getting a torque, and torque is RF sine phi. So the torque that is exerted by this is how far away it is. Now be careful of that. It's not R. It's not the R here. It's this R. It's how far away from the axis of rotation this force is applied, and it's applied a distance d. So that is d. The force is a constant F, and it's the sine of the angle between F and D. Now, F is really like kind of into the page, and then your D is this way, but that is a 90-degree angle between those. So that makes that a 1. So there's my torque. My torque is dF. But that doesn't help me to find omega, right? So I say, well, what else is torque? Well, torque is also I alpha. And so if I said, well, it's dF, and that equals IP times alpha. So then I could divide by IP, and I say, hey, alpha is dF over IP. Now, you know, as we've muddled around with this whole torque thing and still haven't found omega, which is what I was supposed to be finding, but I know now I've got alpha. And so the great thing about that is I've got alpha. I know that I start from rest. I'm looking for my final, which is omega p, and I know that my time is, well, time, because that's what I'm leaving it in terms of. So I see a first kinematic. I see omega final equals omega naught plus alpha t. Omega final is omega p that I'm looking for. Omega naught is 0. Alpha is dF over IP, and then t is delta t. So there's my equation, or there's my expression, dF over IP delta t. And there's my final velocity of the wheel, or of the platform. On B, it says, well, what is the kinetic energy of the platform when it's there? And it says, express your answer in terms of all of this. Well, this thing is rotating, right? It's not rolling. It's not translating. So I don't get the 1/2 mv squared, but I get the 1/2 I omega squared. And so what I have to do is I plug in the I, which is IP, and the omega that I have here, which is dF over IP delta t squared. And there's no reason you have to leave the delta t out here by himself. He can come up there and play with the d and the f. It's just the way that I wrote it. So we'll go ahead and clean this up just a little bit. I don't know if it's really necessary, but I got IP over 2 times all this stuff squared, so that would be df, d squared, f squared, delta t squared over IP squared. There. Now I'm going to cancel one of the IPs, and so if I want to clean this up finally, my kinetic energy is equal to d squared, f squared, delta t squared over 2IP. A lot of letters, but not really that difficult to do. Just plugging it in and getting it all lined out. All right, on C, On C, it says derive the expression for the angular speed of the wheel when we've gotten here. So the wheel has been attached to it and it's been spinning and speeding this platform up, and we want to know what that velocity of that wheel is. Well, there's not really a way to say, like, what did the wheel start at and how much did this apply to it. But what I do know is when they are moving and they are touching each other, that both of them must be moving with the same linear velocity. So the velocity of the platform must equal the velocity of the wheel. And we know that velocity is r omega, right? So for the platform, our r is d, because that's how big our platform's radius is. And our platform is moving at omega p. Our wheel has a radius of r, and we don't know what omega of our wheel is. That's what we're looking for. So we're just going to divide that through by r. And so our omega of our wheel is going to be d omega of the platform divided by r. And all those answers, as I was glancing down here to see, my answer has to be in terms of d, r, omega p, and physical constants, which would be g. So I don't need that. So there's my velocity of my wheel. Okay, now we change our situation just a little bit. And we've got this thing spinning and the wheel off, and so it's spinning at omega p, and then we take this other one and we just plop, like pancake it right on top of it. And it says this has the same rotational inertia as this does. And it says, well, then they observe that they start moving together at omega final, and it says, what's that omega final going to be? Well, you can kind of intuit this and say, well, now I'm going to have two of them, so it should be half as fast, right? But where do I get that? Well, it's conservation of angular momentum. L naught equals L final. In the beginning, it was just the platform moving at, so it was I of the platform moving at omega of the platform. But in the end, they're together. There's two of them, so it's 2I of the platform, because that's your total I. And then it's moving at omega final, and that's what we're looking for. So we'll divide by 2IP. And so then IP goes away, and we get omega platform divided by 2 is omega final. Okay, next page. It says, okay, now we're going to use this rotating platform, which has got an IP of 3.1, to determine the rotational inertia of this unknown object about a vertical axis that passes through its center. And so the platform is rotating, they drop this other object on it, and they're rotating together at omega final, and here they've repeated the trials, and so here is a graph of omega final to omega initial. And it says, on the graph on the previous page, draw a best fit line for the data. Okay, I'm not going to draw on my page because, again, this is my original, but there's my best fit line. Okay, something around there, and I'm just going to draw that straight line. Okay. All right. Now, using that straight line, we're going to calculate the rotational inertia of the unknown object. Oh boy. Okay, so I know that I'm going to go back to what I just did, sort of. And I'm going to say, well, I know that, what is this, E2? I know that angular momentum must be conserved. So initially I've got the I of the platform times omega of the platform, which is going to be omega initial, and that's going to equal the I of the platform plus the I of the unknown times omega final. So they're wanting me to use this graph that I did to calculate that I of the unknown. So if I look at this, my graph is omega final versus omega initial, and it's a straight line, and they want me to use my graph, so obviously they want me to take the slope. Okay, so I need, what is slope? Slope is going to be omega final over omega naught, so I'm going to get that over here. So what I'm going to do is I'm going to divide by IP plus IU omega naught, IP plus IU omega naught. And what that's going to do is it's going to cancel this side, it's going to cancel this, and so I'm going to get IP over IP plus IU is equal to omega final over omega naught, which is the slope. Okay, so anytime I need slope. Now, I know this value, this is 3.1 over 3.1 plus IU is equal to the slope. Now, if I want to go ahead and figure it all out, I can, but I'm just going to leave it like this. I'm going to calculate my slope, and then I'm going to find IU. So I go to my graph to find my slope. So I put my best fit line on here. And what I'm going to do is look for some points. So I'm going to use this point right here. That looks like a good intersection. So it would be 3 and 1.2. And then I'm going to go and find another intersection. This one looks pretty good. That's going to be 6 and 2.6. Okay. So when you draw your best fit line, just, find some places of intersection. So my slope is going to be 2.6 minus 2 over 6 minus 3. So that's going to be 0.6 divided by 3. So that's going to be 0.2. So that's my slope. Okay, they're the same units, so they're just going to cancel out and be 0.2. So 3.1 over 3.1 plus IU is equal to 0.2. So I'm going to do kind of a little algebra trick. I'm going to multiply both sides by this bottom and divide both sides by this. Basically, that means I'm just going to switch places with these two. So I get 3.1 over 0.2 is equal to 3.1 plus IU, and then I'm going to subtract 3.1 from that. And so I'm going to get IU is equal to 12.4 kilogram meters squared. And that's my I of my unknown object. All right. Now, these are checkbox questions. We like checkbox questions here. The kinetic energy of the spinning platform is dropped before it is dropped is Ki. The total kinetic energy after it reaches the angular speed is K final. What is true about K final and K naught? Is one bigger than the other, or are they the same? So I think about this and I think, well, I'm going to drop something on top of something else. And because I am, they're going to stick together. And when they stick together, that becomes what is known as an inelastic collision. And so that makes my answer extremely easy. My K final is going to be less than my K initial. And I know this because this collision, whoops, if I can spell collision, is inelastic. I know this because they stick together. And kinetic energy is lost in inelastic collisions. Okay, not all of it is lost, but we lose some. So we know that it's not conserved, because that's how we tell when they ask us, is a collision elastic? We go, well, does it have the same energy in the end as it did in the beginning? And if it does, then yes, it's elastic. If it does not, then no, it is not elastic. And so this one, we know that it is an inelastic collision because we already know they stick together, and so therefore they cannot have, you cannot have the same, and you sure can't create it. You'd have to have an external force to change your kinetic energy doing work. So we don't have that. So it's got to be less than. All right, then they say, well, what if, though, they observe that the center of mass of the object is not really lined up with the axis of the platform? So is our experimental value that we got greater than, less than, or equal to the actual value of the rotational inertia? Okay, so my rotational inertia, here's the axis of rotation, but what if, whoops, I land it where the axis of rotation is here? Okay, what I've done is I've now changed it. So I've moved it a distance h. And the reason I call it h is because we have this whole parallel axis theorem. Oh my goodness, let's try that again. Parallel axis theorem that says I is equal to I com plus mh squared. So I com is what it is if it's going through the center of mass, but if I miss, it's going to be increased by this. So because it's going to be increased by that, my my experimental value is going to be greater than, because it is going to raise my I up. So that's going to change it, and we're going to get a greater than, and that's because of this.